All right, good afternoon, everyone. I think we can get going. We're almost up to 50 attendees, so that's a good start. Welcome to today's SMRI webinar, which is on how to get more out of your SMRI-NIRS system. As you would know, the NIRS system is working in all South African factories for a number of years now, having replaced quite a few conventional wet chemistry methods. And as of the end of this year, we'll also have the NIRS system in at least 9 Southern African factories. So today's webinar is presented by Stephen Walford. I'll be very surprised if he's a stranger to you. He's been at the SMRI for more than 30 years now, and he is, of course, the NIRS project lead as well. So Stephen, I will hand over to you. Please tell us how we can get more out of our NIRS system. Stephen, you are muted.
Now you can hear me. Sorry. There's a picture of me. You can see me. I'm going to disappear now while I take over the screen. Okay.
Perfect.
Okay, cool. Let me just see what I can do here. Can you see my screen or not?
It's still coming up.
That's weird. It worked just now, didn't it? Oh, there we go. There we go. It's taking a while for some reason. Must be all the people watching. Can you see that now?
Yes, we can see your screen.
Okay, there we go. Cool. Great. Thanks very much, everybody who is watching today. Welcome to this, I don't know, it's our 4th, I think, webinar this year. We're going to focus, obviously, on the NIRS technology, and I'm going to try and touch on some of those items that are up on the screen there, and hopefully we'll have some questions and answers at the end, and we'll all go home very happy. So let's see what we can get out of this. But before we start, let's just talk a little bit about the basics of NIRS, just in case anybody is not up to date or not aware of how this thing works. This is the NIRS that we are all familiar with, which is a Brooker MPA. But the basic part of any NIRS system are these 3 things here. The first is the NIRS source, which generates infrared energy. It comes along, goes through in our particular case, a sample cell of some description. The sample inside that cell will absorb some of the energy. And you can see the energy on the left-hand side here is a bit less than what was going in over here due to that absorption. And we have a sample detector, which measures how much energy is being received at that point. And from that, you can work out how much has been absorbed by the sample. In our NIRS, these 3 things are in these parts of the actual instrument. The source is on the right-hand side here. In fact, if you put your hand there, sometimes it's a little warmer than everywhere else. The cell is just off the middle, to the left of the middle. And if you were to take all the covers off, inside you would see the detector is sitting just to the left of the side here and slightly in. There's also a laser in there, but we don't need to worry too much about what that laser does at the moment. So when we take this energy and put it through our sample, we get a spectrum. And this is a typical spectrum. We measure them in wave numbers, and that's just a spectroscopy type number, and how much energy it absorbs over here. And you'll see there that for any particular wave number, there is a absorbance. So for 7,000 here, it's whatever that is, 1.8 or whatever. Here is a small portion of that whole spectrum. You can see it runs from 5,400 wave numbers, which is over here somewhere, up to 5,300, which is a bit less over here. And you can see it runs from 0.5 down to 1.5 or up to 1.5. So in fact, it's this little portion over here It's that bit there of this whole spectrum. And in fact, there's about 2,200 data points for any one spectrum that we collect for our samples. And that's an awful lot of information, because the moment you start using lots and lots of spectra to develop calibrations or do comparisons or anything like that, it's a lot of data. It multiplies very, very quickly. So we need to just remember that our software has to handle all of that. What does that software do? Well, that information which is collected, in this particular case, our little bit here that I've shown, there's obviously more than that, goes into a piece of software which is generally known as a chemometrics piece of software. In that software, we have the ability to access a prediction equation, which has been developed using that same chemometric software. We apply the prediction equation to that spectrum, and we predict, based on the shape of that spectrum, what the bricks would be, the pol would be, the sucrose would be, whatever. And it could be anything else in there. So that's what we see as the final end result. We use that information, obviously, in our factories. Now, what is it used for? Where is it used, the NIRS? Let's be honest, the sugar industry has been very slow to catch on to NIRS. NIRS has been around for 30-odd years, and it's used in things like animal feeds, milling and flour, grains, pet foods for raw materials and finished products, animal feeds, moisture, protein, fiber, starch, and so on. The grains, in fact, in the 1980s, NIR was being used to sell grain as a commodity worldwide. So we are way, way behind in some respects. But it's a very broad spectrum of industries. Petrochemicals, it's used for blending oils, meats for measuring fats, pharmaceutical and medical applications, pharmaceutical checking what's in a tablet, how hard a tablet is, things like that. And medical, they can measure glucose in your blood without sticking pins in you, or needles rather. They can measure what goes on in the brain. There's lots of things like that. A big industry is the pulp and paper industry, using NIR for process control and also for moisture in the feed to the pulp and paper industry. Another big user is the plant breeding industry, and it's used here at SASRI for exactly that, to help with the plant breedings. Now, if we want to use the NIR, how do we do it? Well, there's a lot more than just putting a sample into an instrument that we've got over here and getting a result out. Like any analytical technique, the results that we get are very dependent on this bit here, the sampling bit. I have to assume that the people in the sugar mills know how to sample, so I'm not going to discuss that one at all. But we take that sample and we will, depending on the sample, we'll either just filter it or we may just dissolve it. So any of the samples from syrups through to final molasses will end up being massed, okay, on some type of balance. Of course, there's an assumption there that our balance is level, our balance is being calibrated correctly, that the operator knows how to use the balance correctly, that numbers are transferred from the balance correctly. There's a whole lot of things that could go wrong there. We then come along and we take that sample that we've taken off our balance now, weighed or massed, and we have to mix it and dilute it and dissolve it. And this, again, is another problem, because we're assuming that good lab practice is being followed. So we have to assume that the sample is well mixed, that for something like an A mesquite or a B mesquite or a C mesquite, those sugar crystals that are inside those mesquites are dissolving and are totally dissolved before you take the sample to the instrument. They must also be well mixed, because if you just leave it at the bottom, the sugar crystals are going to end up forming a much more concentrated solution at the bottom. So there's lots of things that could go wrong at this point. We then come to what we might think is the easy bit, and that is, well, let's put our sample into our cell. Well, yes and no. If you don't follow the SOP correctly, you may have carryover from a previous sample because you haven't flushed it through correctly. So that's another point where something can go wrong. We then get the instrument, we put it in, and we get our final result over here. From our experience, from SMRI's experience, the biggest issues is, ignoring the sampling, is the massing, the mixing, and putting it into the cell. It's very seldom the instrument. It's always one of these three things here, which is a problem with somebody who may experience a result that just does not seem right. So if you are experiencing untoward results, please check that your analytical procedures are being followed correctly. I'm just going to very briefly, quickly, we do train you on this, but how do we know that the instrument's working correctly? You can go to the screen of your software, the Opus software for the Brooker MPA, and in the right-hand corner you'll see this little light shining, which can either be green, amber, or red. If it's green, it means everything's honky-dory, the instrument's running correctly. If it's amber, it means something may be going wrong. You might need to check it. If it's red, it means the instrument's not going to work at all because something is very wrong. And if you click on that little button there, you get this screen here, which pops up, which actually shows you the main components within inside the NIRS instrument. So in our particular case, because it's a Fourier transform instrument, we have a laser, we have a source, we have our interferometer, and so on. If any particular one of these is wrong, it'll come up, instead of saying okay, it will actually say there's a problem here. If you go and click on it, it will open up another screen, which then goes through a whole series of checks to check that your instrument is running correctly. I don't want to say any more than that at the moment. If you need more information, go and have a look at your Opus manual, which is included in the software, or go to our website and go and download some of the training manuals that you should have already got. But if you don't have it, then fair enough, go and download them and see how to do it. Right. So the question is, though, you can do all this. How do we at SMRI know that your instrument is running correctly? Well, one of the things that we do is we have what's known as a validation scheme. The validation scheme is a pretty important tool to help us, because what ends up happening is that we can send you some samples and we can check that the NIRS and the technology is functioning correctly as a whole. We can get scans from your instrument to add to the existing equations because we know what the conventional results are, and they can help build up the robustness of the prediction equations. And then finally, one of the things, we've been running this for 2 years now, 2 years, is it helps. Something that we've picked up is we need to check that you as the user are using the correct equations. So we can pick that up as well, because all of that information, a lot of that information is in the scans that you might send to us. Right, how do we do this? Well, before I do that, there is one other thing you can do with your instrument, and there are 2 tests that can be done: the operational qualification and the performance qualification tests, which actually tell you that the instrument is functioning, but it doesn't tell you that it's going to predict correctly. Okay, that's all it does. So we use this validation scheme to make sure that it's predicting correctly. So the first thing that we do this year, we introduced this sample, which is been very useful already, and that is a synthetic juice sample. We prepare a synthetic mixed juice sample by mixing known amounts of sucrose, glucose, fructose, potassium chloride, and a bit of color and all sorts of things. And we can use that to check that your instrument is running correctly. And I'll show you how in a moment, okay? Because there is no sample preparation required. That sample is diluted, it's preserved. We've worked out how to preserve it. It comes in a sealed bottle, just like a vial full of COVID-19 vaccination material or whatever. And you crack it open, you take the sample and you push it into your NIRS cell. Assuming you follow the SOP correctly, it is just going to tell us whether your instrument's running correctly. The second sample that send, or more than one sample, typically it's 2 samples or 3 samples that we send, are process stream samples, typically A mass wheat with a molasses, or a B mass wheat or a B molasses, and so on. It's normally some combinations of those. And we ask you to prepare those samples like you would a sample out of your mill. So that requires the sample dilution. Now, we know what the concentration, or the conventional concentrations, conventional analysis results are of that sample. In other words, we know the pol, sucrose, glucose, Brix, whatever. And we can check on the scans with the concentrations that we get from them how well you've done that sample dilution and whether you're doing it correctly or not. So we then ask that you send those scans back to us and we can check them. And what we do is we can check them using exactly the same equations that you have in your mill instrument, because they're all the same equation at the end of the day. So we have exactly the same equations that you have. So we can check the pol, the Brix, the whatever we get out of each of these samples and check them according to our results, and we can work out whether there's something wrong or not. And let me show you what I mean by this. Here are the results of the Brix samples from that synthetic sucrose, one of the synthetic sucrose samples that we sent out. There's 15 results here. And what you can see, just looking at it, is the concentration of the Brix on the bottom there. They're all clustered round the 12.3 to 12.55 or something mark. They should actually be all pretty close to each other, and they are, other than the two on the left that look like there's something a bit odd, and there's one on the right which also looks a little bit strange. They're almost like outliers. So we need to see how can we use this information now to help us work out if there's something wrong. So just remember that this synthetic juice solution didn't require any dilution or anything. This is just simply putting it into the NIR. We then apply some robust, what's known as robust statistics to these numbers, and we can calculate the robust mean and the standard deviation, and that's what this red line is here. Okay, so this is the mean of the data when I apply robust statistics to it, and you can see it's actually worked out pretty well. It looks sort of in the middle of all of them. It actually comes out at 12.44. We also can calculate the robust standard deviation, as I said, which actually was 0.14 in this particular case. And using those numbers, you can generate a normal distribution. In other words, this is what the normal distribution of that set of data based on the standard deviation and the mean over here is. We can generate this normal distribution, which is what everybody's used to. They all think, you know, we have a normal distribution like this. And you can see it actually works quite well. It's slap bang in the middle over here. And you can see the majority of these results sit in the middle at this point here. The pink shaded portion on the left and on the right here are the regions that are plus and minus 2 standard deviations away from the mean in the middle over here. So in theory, 95% of all results should fall inside that white space and not inside the pink space. And in fact, clearly those two on the left are really very dodgy because they're way out. They don't fit into this subset at all. This one here is close to the edge. It may fit in, it may not fit in. At the moment, we're still using plus or minus 2 standard deviations. We may change those numbers as we continue with this program, but that's what we've started out with. So why do these give a problem? Okay, that's the question you've now got to ask ourselves. So we do a little bit more investigation. And one of the nice things about getting the scans back from you people in the mills, those who use it, is that there is a whole lot of metadata in that scans. And that metadata tells us all sorts of information about how the instrument was functioning at that point in time. So we can use this to check immediately if there's something wrong. And one of the things it does, it measures a couple of different temperatures within the instrument. Okay, so what I've done is I've plotted those same concentrations against what in fact is the lab temperature on the left-hand side here. And you can see immediately that those three samples have higher temperatures than all of the others. So part of the instrumentation is a lot warmer than everywhere else. Now, you may think, well, is that such a big deal? Well, it is a big deal, and I'll tell you why. Because this thing makes a lot of sense, because our samples are dissolved in water. That's just what a sugar mill does. It dissolves sugar in water. And water, the NIR spectrum of water is affected by temperature. Okay, so the shape of that curve that I showed you earlier actually, or spectrum, changes fractionally with temperature. And the software, the chemometrics, can pick up that change quite easily. In fact, somebody told me quite a few years ago, a long time ago now, that it is probably the most expensive thermometer that you can buy at the cost of a NIR instrument. But it's pretty accurate because it can pick up temperature differences of less than 0.01 quite easily. Anyway, that's not the problem. I've now put on there two red lines. And those two red lines represent, well, let me go back one step. When SMRI developed those equations, we were aware of this problem of temperature and water. So one of the things that you can do, instead of saying, well, let's try and make everybody run at exactly 20 degrees C, or whatever it is we want to choose it at, we can make the temperature a variable and include it in the equation. And that's what we did. We, in the many thousands, I'm talking nearly 30,000 spectra that we have got in our different equations, they've all been scanned at a temperature range of between 19 and 23.5 or 23.8 degrees. We've allowed the temperature, we purposely turned air conditioners off, let the room warm up, and so on, so that we could account for typical mill lab temperatures, right, between 20 and 24 degrees. And sure enough, you can see these labs here are running pretty well because their temperature is obviously below that 24 degrees. These three, in this particular case, had a problem. Their lab temperature was higher, and therefore it predicts incorrectly, which is significant. So the moral of the story is, if you want to get the best out of your NIRS, you need to make sure the instrument's located in an adequately controlled temperature environment. It doesn't matter if it runs up and down by those 3 or 4 degrees here. That's not an issue. It just makes sure that it stays within that and not outside of it. Otherwise, your predictions may well start drifting fractionally. So just be aware of that. So that's the first sample, the standard, the synthetic mixed juice that we supply. That's one of the things that it can help us with. The second sample, the one where you go along and dissolve it, we use a normal validation scheme, proficiency type scheme, to check if that you're using the NIRS and preparing the samples correctly. In this case, we use a Z-score system, which is what I've got here, where we take the results that come off the NIR, compare them to means and to the conventional analysis, work out the differences, and then work out from the standard deviation a Z-score. And Vaneshri Pillai actually described this in a couple of webinars ago. If you want to go and find out a little bit more about how it works, she was using it for conventional analysis, but we do exactly the same thing with NIR. This is one of the graphs that we draw. This is each of the different mills, so that nobody knows whose mill is what, so that nobody can be accused here. And they actually are all working pretty well. I look at this picture because I want to make sure that there is a normal distribution in this shape across the sample results that we get. If, for instance, these were all hugely negative or hugely positive, it means there's something wrong with the sample that we sent you. This is telling me that this particular sample that we sent you was actually fine. There was nothing wrong with it. It happened to be this is the bricks of a masquite that we sent. And so what is important to you, though, is not so much this picture, but this picture here. This is a typical Z-score plot that you're going to get. And what is important to any lab is these lines here, the green line, the orange line, and the red line. And you can see when we calculate a Z-score, right, the Z-score has got nothing to do with the actual bricks that you measure. I'm going to show you that in a minute. But the Z-score is a statistical value that shows you how good you are, well, not how good you are, but how well within the normal statistical regions you are for that particular analysis. So from statistics, if you are between the 2 and -2, in other words, the orange lines around this green line here, what it indicates is that you are statistically working very well. There's nothing wrong with it, okay? If you're between 2 and 3 or -2 and -3, up the red line there, what that means is that there's a statistical chance that you could be inside that region 1 in 20 times, which comes from stats, the 95% on a normal distribution curve. And so that there indicates that this particular guy could well, there's nothing wrong with it. It may well be just the 1 in 20. So all it's telling you is just look out the next time you get a result from a proficiency test, make sure you're not in the same region. Make sure you're not between 2 and 3, because then it's telling you that maybe there's a little bit of a bias there, okay, that you need to be having a look at. There may be something else. There may be something wrong with your balance. There may be something wrong with the way you're dissolving or so on. But if you're continually inside that region, then there is something wrong. You need to look at it. If by any chance you happen to be above the red line, then you need to be pretty quick and go and have a look and see what's going on, because that statistically means you are the real outlier. There's something wrong. Statistically, it doesn't make sense that it should be there. You need to go and have a look at your balance, the way the guys are operating. Maybe it was a transcription error or something like that. So just be careful. Just look for something like that. You need to make sure that you can go and have a look at some remediation straight away. Okay. The other thing we do is we compare the difference between the NIRS result and the conventional result. So that's what I'm showing here. This is the conventional result. In other words, in this case, refractometer bricks minus the NIRS predicted bricks. And these orange, whatever color lines they are, not really orange, but anyway, they're close to it. They are the reproducibility values of the conventional analysis. In other words, if I took a sample and I went and analyzed it 100 times, I can calculate there would be a natural spread of results, and I would find that 95% of the time my results would all fall in that difference there between the mean and the result that I get. So I can use the same reproducibility values for the NIRS because they are based on wet chemical or conventional analysis results. And so the difference between them should be within that range that I have here, that I've shown here. Again, the thing here, I look at this one and I say to myself, well, this is that guy again, that same lab, and he's just fractionally outside of that. Well, that may well be our 1 in 20 chance that he's outside. But if he's continually there, I need to go and start looking at something here. So the validation scheme not only shows how well or not how well your instrument is running or functioning, but it also gives by using these samples an indication of possible problems with lab procedures and equipment calibrations that you might need to go and investigate a little bit further. Okay, so on the next slide, I hope if you've got any questions, just type them in onto the chat and we'll try and answer them as we go along. Now, one of the things that people ask me is, what about unbelievable results? It's impossible. This thing can't give me this result. Okay, this is an example of just that. So what I've done here, well, let me go back a step. You've got to remember that NIRS is actually a secondary technique. By that I mean it is based, it's a system which is based on a set of results from conventional or primary analysis methods. So it is going to give a result based on those, but there may well be times when it's fractionally different. And we need to just be aware of that, because we're using a chemometric or a statistical processing of the information from the NIRS to give us that prediction. And I think you need to understand that the predictions work very, very well if the sample being analyzed is the same type as the equation. If it's not the same type as the equation, then there may be a problem. And that's what I just want to show you here. This is an example. Just have a look at this last column here. It says acceptable with green tick and 2 red crosses. That column is what you will see on your Opus Lab software when you do a scan. Okay, it's telling you everything's fine or it's not fine. In fact, there's even one on the front. There's even a little green tick on the front of the NPA, the NIRS instrument, that gives you a green tick or a red cross to tell you, yes, it's okay, or no, it's not okay. Maybe we need to think about this, it's saying. So what I've done here is I've taken some mixed juice and I've analyzed it using the mixed juice equation. Right? So it's predicted 1393, and you see it's in black, and it's got this funny thing here called MAH distance or Milanobis distance, and it's got a limit, and I'll explain what those are in a moment. I then took a final molasses, which has been dissolved by our 15 grams plus 85 grams of water, which will give us roughly the same concentration as a mixed juice sample, but it comes up in bright red. And it's got this other thing here. You see this melanomas distance is now bright red, and this limit is way out. And then I've got another one, which is a mixed juice, but it's actually a water, which has been used to flush. And it's got a trace. Remember, I was talking about it earlier. If you don't flush properly, you're going to have a trace of the previous sample in it. So this water was the first washings and had a little bit of a trace of bricks in it. And you can see straight away, it has another thing. It has this one here called outside. Now, I want to just explain what some of these things are. What you've got to understand is that the mixed juice equation, which was used for all 3 of these, has been developed using mixed juice samples. Trying to apply that mixed juice equation to a final molasses is a problem, because final molasses is nothing like mixed juice. It's got far more fructose, far more glucose in it, far more color, far more ash. It's got less sucrose relative to everything else. It's got far more higher concentrations of gums and whatever than what you find in mixed juice. So the matrix has changed. And the software, the NIR, will pick up that matrix is not the same. And it says, no. This thing is nowhere near, and that's what this Milanobis distance is, and I'll show it to you now, is nowhere near what my mixed juice is. Therefore, I'm going to say this thing is an outlier. The sample is an outlier. It's no good. Right? Similarly with this water, this wash water, it said, oh, no, it actually doesn't look much the same, but the biggest difference is this one here, which is outside. And I'm going to show you what that means right now. So this here is a scan, it's a picture of approximately 100 mixed juice scans that I've taken that were used in the development of the mixed juice calibration, or the front end calibration. And this space this picture is known as a principal component space, right? So I'm plotting a PC1 versus a PC2. You don't need to worry too much about it, except that it's a mathematical technique of taking all of those 100 scans, the 2,200 data points for every single sample, doing a little bit of math to them and comparing them and saying, are they the same or not the same? And sure enough, my first sample, the mixed juice, is this blue one over here. Okay, it fits in beautifully into that space. I now come along and I said, well, let's go and put the final molasses and the mixed juice in that space. And look what happens. Here's our mixed juice samples. Over here is our control water sample, and down here is our molasses sample. Okay, so you can see straight away that this, you see this distance here for our final molasses, 0.05, it's miles away from the component space, what we call the principal component space of our mixed juice samples, and it says it doesn't belong to that set. This is very important, because what it's saying to you is when you get a cross on your result sheet, on your Opus Lab, on the computer, be aware there's something wrong. Just think about it. Maybe reanalyze it. And if necessary, get hold of us. Contact us and just ask us why it's doing this. I just want to show you what happens with the second one. This here is our calibration curve for mixed juice. And there's something like 20,000 spectra inside this thing. You'll notice that it looks like it's going from 0 right up to about 17 bricks, all very well. This is our prediction, it works well. However, if I go and blow this little bit up over in the left-hand corner here, I get this here. And you can see that our result is saying, you know what, based on the scan that I got using the chemometric software and the mixed juice equation, I actually am predicting that it's 0.16 over here. But notice that my curve stops at 0.23. And the reason for that is that the lowest sample, the lowest scan that I have in my calibration set of data is 0.23. And therefore the equation won't go any lower than that. So even though it'll predict, it's warning you, look out here, it's outside of my calibration curve. It's outside of where it's possibly valid. It may be valid, it may not be valid. Be aware of that, okay? So again, you will get a cross on your screen. Be aware of that. Do something about it. Go and take another sample. Go and analyze it again. Maybe the dilution's wrong. Maybe you haven't flushed the system correctly, but do another sample. If it still comes up with a cross there, right, then let us know. And we'll ask you to either send us a sample if possible, or send us a scan along with a conventional result, and we will check it and add it to the equation. So please, please do that if you can. So that's enough about where we are right now with NIR. We've added a few things to it in terms of the validation scheme and how we're using them for that. I now want us to talk or think a little bit about what else can we do. And so one of the questions that I've always been asked is, what else can we add to the NIR? And there's lots of things that people would love to add to NIR. And I'm going to just give you a reason now why some of them cannot be added and some can be added, okay? So last year, the end of last season, early this season, everybody got given a ethanol and bricks prediction for DAC samples. The idea being that previously, historically, ethanol has been an indicator of deterioration. Now, it partly is an indicator of deterioration. It's not an outright indicator of deterioration. And you can go and look at some of the papers that I've written and Sinette's written and so on about this. But this here is very important to some people. So what it allows you to do is you can measure ethanol, okay? And previously, 20 years ago, a lot of mills had their own GCs, and they would analyze the DAC sample for ethanol. and they would then go and get the bricks, and they would say, oh, this consignment of cane had a very high a very high ethanol on bricks, and therefore it is possibly deteriorated and maybe adding problems to the factory. Sorry. However, many labs no longer have that instrumentation. They don't have the resources to run such equipment. And so the question was asked, can we do this? Can we use NIRS to do this analysis far easier, far quicker? Yes, you can, sort of. And that's what we have supplied to you. Okay. So this is a graph of the calibration curve. Now, I just want to show a few things. This here on the bottom is the actual concentration on bricks. This here is the predicted concentration on bricks on the left-hand side here. If you look at this graph, you'll notice that there's an awful lot of scatter around this graph, around this line, okay, which is the equivalence line. And that is a slight problem, because that scatter is due to the fundamentals of physics and due to the fundamentals of how that impacts on the NIRS, okay, how you scan a sample. So let's think about this. If I take a 3000 ppm on bricks sample, back sample, right, that's equivalent to 180 ppm, parts per million, of ethanol in solution. That for roughly a 6-brick solution, which is what you're going to get for a DAC. That's equivalent to 0.018% in solution. NIRS has problems quantitatively differentiating less than 0.1%. And the reason for this is sheer physics. There isn't enough ethanol in our solution to make a huge impact on the absorbance. And so there's very little difference between a sample that has 0.018% and a sample that doesn't have 0.018%. And so that's part of this scatter problem around here. So what that means is that if you come along and you put in a sample into your NIRS and it gives you 3000 ppm, or let's take our 5000 here. So if I come along and it's really got 5000 ppm on bricks, it could be anywhere between 4500 and roughly 6000. Okay, so it's got about a 1500 ppm scatter around it, and that's just plain physics. You can't get away from that. However, what it does do, this equation, is the method can still be used, because if you've got supposedly cane which is not deteriorated, you will get somewhere in the region of 3 to 4,000, maybe 5,000 ppm on bricks of ethanol in solution. If you've got deteriorated rotten cane, there is no doubt that you're going to get 11,000, 12,000, 13,000 ppm on bricks. This equation will differentiate between those two. So the quantitative result may be fractionally wrong, but the qualitative result saying you've got a low number or a very high number is correct. And therefore you can use it as an indicator that, gee whiz, maybe the cane that I've got coming in right now has got a very high ethanol concentration or a very low concentration, and maybe you can do something about it. So even though there's this huge scatter, it does qualitatively tell you I've got good or bad juice coming into the factory in terms of ethanol. Okay, so that's one of the recent additions to the NIRS. I now want to move on to what can we do with this. Okay, as I've just mentioned, there are two ways of looking at NIRS scans. We can either do it quantitatively, like this graph that I've just shown over here. We can try and say, oh, it's got exactly 10 bricks, which is what we do with most of our scans, okay? Or I can say, you know what, this material is good or this material is bad. And that's what this equation is sort of doing, okay? And I want to show you some applications that we're looking at in terms of doing that qualitative result. So this here, in our research program, Dr. Sinet Nell and I are investigating the possibility of using NIRS for the classification of cane entering into the mill in a deteriorated or non-deteriorated form. Okay? So this picture is again a principal component space for cane that's undergone deterioration in a very controlled condition. Right? So we put it in a lab oven at a fixed temperature and whatever, and we know how well it is deteriorating because we actually add bugs to it to make it deteriorate. So the nice thing about this is all we've done here is we've taken some of that cane. We haven't analyzed anything. We have simply taken some of the extract and put it into the NIR. And we've said, on those results that we've got, what can we do in this principal component space? And guess what? The software is able to classify very clearly the different groups of days of the samples. So immediately there is something here which is telling us there is something different between the first couple of days. A bit later, something else changes between days 8 and 10 or so, and then something else changes a little bit further on. So there is something changing in the juice. I have no clue what it is. Neither Sinet nor I have a clue. Well, we sort of have a clue, but we have not told the software what it is. There is something fundamentally different in the NIRS scans from this one to this one to this one to this one that can be picked up quite easily. Okay, so we've done a similar idea where we've now gone and looked at the volatiles that come off deteriorating cane. And notice what else we see here straight away. Under these controlled conditions, again in a principal component space, we can see samples that are totally grouped at the bottom here and another group that are from days 11 and onwards. So you can see that they are classified into earlier and later samples. So as an aside to this work, using these results is helping us to see what the impact of time has on the production of the combinations of deterioration products. Not like looking at ethanol only, which actually only occurs as part of that deterioration, but across the whole spectrum of compounds that are causing that deterioration. And this is just such exciting work. So hopefully it's going to help us explain why ethanol and dextran and mannitol and lactic acids by themselves are not good indicators of cane deterioration. And so we're trying to use this as an indicator eventually of cane deterioration using the NIRS. One of the other things that we've been looking at, something totally different, and a lot of you already have this on your instruments. This is a possible future application, and that's the use of the reflectance part of your NIRS. Some instruments have this on, some people bought it with it. And what happens here is that the infrared light actually comes out of that little hole there, that little aperture, and you place a sample. In this particular case, let's imagine that sugar inside there, and the bottom of this little dish is transparent and allows the NIR energy to come up into the sample, bounce off the surface, bounce off the crystals, and go back down to a detector that is sitting underneath. What happens is this particular dish is actually rotated in here to make sure that you've got a mixture of surfaces that are exposed to the light to give you a much better spectrum at the end of it. This is the type of accessory that's used in grain labs, flour labs, and in fact, in most of Europe, a lot of the milling companies are connected to one central laboratory, and all the NIR instruments are run off that main lab's instrument, and they just put their flour in here, put it on here, scan it, and go and change their process control or whatever they need in their milling lab. So we've managed to develop some equations for pole, moisture, one or two other things in raw sugar and white sugar. And this here is the result of about 1,500 scans of raw sugar for pole. And what I've done is the red bits are the histogram. In other words, what I'm showing here is the difference between the conventional result and the NIRS result, and then just added up however many times that difference occurred. Okay, and you can see that it's going to come out as a normal distribution, which is what that blue curve is, quite happily there. So the range of these differences is clearly well described by this normal distribution. And you might think that, hey, you know what, this method actually works pretty well. Look at that. Why can't we use this? Well, there's a major problem with this. And this is one of the things that it's all great saying, oh, we can do it. Yes, we can do it. Are the results useful to you? And this shows one of the problems of using a technique such as this. If we go to conventional pole, the repeatability difference between two scans, between two results on the polarimeter, pole is incredibly precise. And we've got used to that, especially for our pole for raw sugar. And the reproducibility difference is plus or minus 0.05 units. 0.05. Okay, so if you go and sell sugar, typically that'll be the limit that they will allow. If you say my sugar must be 99.3, and you supply sugar which is 99.36, then that's not the sugar you were meant to supply me, whatever. Okay, the 0.05 is very, very important. So these green shaded areas here on the graph show where the difference is greater than 0.05. And you can immediately see what our problem is going to be. More than 53% of all the samples that we've scanned and got a result for are greater than the acceptable differences for the analysis. So what this means is that if you were to analyze a raw sugar and obtain a conventional result of, say, 99.5, there's more than a 50% chance that the NIRS result could be anywhere between 90, hold on, let me just put it on, I'll put it here, 99.3 and 99.45 and 99.55 and 99.7. So imagine what that's going to do to your recoveries, to your sugar balances in your factory, to your income, definitely in the short term. In the long term, it's not going to affect those because on average, the difference here is 0. So that's fine. So if you run this over a year for your factory balance, it's probably going to work. But some batches are going to be higher, some batches are going to be lower, and that could lead to a process issue. Because if you suddenly come along and say, oh no, the stuff coming out of the centrifuge is 99.3, we're washing too much or something. Turn back on the wash water and the color goes up, or whatever the case may be. So we need to be very careful about just taking these types of methods and applying them in the sugar factory. We have to be very careful that we make sure that everything is running properly and that some of those issues are being addressed. But this is not an easy issue to solve, I must say. So I've hopefully given you an idea of where we are within NIRS at the moment, some of the things you can look out for, some of the things that have just been added, and some of the things that we are looking at as possible future benefits for the industry. At that point, I would just want to thank you and say, are there any questions? Thanks very much. Sean, back to you. Let me see if I can, or maybe you can take the screen.
It's fine, Stephen. You'd have to stop sharing. See, I've got a bit of an echo. Stephen, thank you very much for that presentation. It was very, very useful. I certainly picked up on quite a few troubleshooting guides, and I'm sure that our attendees would have as well. There are a couple of questions in the chat if you want to have a look at them, but I can just quickly read them out for the benefit of everyone. So in answering the first question, maybe you can just comment on what are the predictive equations that you're working on currently? And in doing so, you can answer Neville Lewis's question. So Neville comes from Genovan usually, which is a member mill in Mozambique. Though recently I've been told he's been doing some work at the Ullets refinery. And he wants to know whether there's been any efforts in determining the sucrose content in wastewater or in condensates, so basically effluents. And is there any progress on developing refinery equations for refinery liquors? And his third question is about what properties can be analyzed on crystallized or crystalline sugar, which I think you've answered in part.
Okay, so there's three bits to the whole question, I suppose. The first bit is well, let me go back to the point that I said in terms of the wastewater. The issue is that, as I've mentioned, the concentration of typical wastewater sugars is going to be. Are we talking about wastewater from a mill, or what, or sugar traces? Is that?
Yeah.
There's
So,
going to be a slight difference.
Stephen, I think it's a sort of general question. It will refer to boiler feed water.
Okay.
It will also refer to mill effluents as well.
Okay. Let's talk about it generally. If the concentration of the analyte that you're interested in is less than 0.1%, basically NIR will not give you a quantitative result that is really good. It may give you a result, but it would probably not be that great. Okay. However, as I showed you in the ethanol one, the fact is that you may be able to say, I'm prepared to accept a good water and a bad water, or accept it as a differentiation between good water and bad water. And that we can pick up. That, exactly like I showed you with the cane deterioration, we can pick up qualitatively it's good and bad. And I think that's the way that we need to think about it going forward. So if I think of, so for instance, everybody keeps asking me for dextran. Dextran in sugar. Well, dextran in sugar is 150 ppm. Dextran in sugar, that's 0.01%. Okay, it's never going to work. However, you could have, let's say you've got a high dextran coming into your factory in the juice. We could have a thing that says this is a good juice or this is a bad juice. Okay, it will pick that type of differential up quite easily. So that we can do. In terms of equations for the refinery, there are equations for the refinery. However, what you've got to remember is that some of those refinery streams are incredibly pure. They're very high purity streams. And so the moment you get to the high purity issue, you're going to have what I showed you on that picture of the reflectant sugar. So for control purposes, it's going to be a bit of a problem. However, for the slightly lower purity material, right? And so if you're looking at the jets or the liquors or the things like that, they work very well. They do predict. So those work. So that bit will work as well. What else is coming down the line? Well, you've seen some of the stuff that we've got there. I think there's a couple of things we need to think about here. Number one, we need to make sure that everybody in the industry is on board with what we've got at the moment, and everybody in the industry runs with it, because we can then say, right, what is the wildfire in the industry that we need to sort out now, or whatever, and get some input from that. So we need to go back to the steering committee for the NIR and actually apply some pressure there, which is where some of our direction comes from as to what to do. I don't know if that answers the question.
It definitely does. So if you can just comment, I see there's a comment from Janice as well, just to remind you about the refinery equations, if you can comment on that.
Yeah, I just did. The refinery equations are fine for liquors, for the melts and the liquors.
Okay.
They work fine.
Not so much so for the sugars, right? Because of
sugars, that high purity is a problem. In fact, for NIR will not work for any product which is incredibly high purity. By that I mean it's a 99.9% pure material.
Sure.
Because yeah.
All right, Stephen, that's great. If we can move on then to the next question, it comes from Tulas Ngenwa. I remember the last time he was from Ilovo Mia Bank, and I think that's quite evident from his question. And that, has the NRS been trialed in the fermentation industry? So what about beer analysis, and how does it perform?
Yes, it does. It works very well. I've seen it working perfectly in a, what's the Danish brewers? Heineken. No, it's not Heineken, it's the other bunch. But I've seen it working there. They actually use it to control their factory.
Okay.
So great. Yes, it does work.
And of course, Stephen, we know that it works on sugarcane molasses. So
it works on the molasses perfectly.
Yeah.
It'll work on fermentation broths very well as well. It does work on fermentation broths. There is some work in the world doing that. Yeah.
I agree.
So for me, that would be okay. I can't say what we should be doing or shouldn't be doing, but for me, that would be a win for a couple of companies within the sugar industry, because they already have fermentation plants.
Sure.
And that's somewhere maybe they need to all get together and say, you know what, let's go to SMRI and get them to do something for us.
Yeah.
But I can't say that, but you've heard me say it.
So Stephen, maybe you can just comment on the fact, or I will, basically, that each one of our members is represented on steering committees for the NRS project. So certainly any requests from millers can come through those steering committee members as well.
Yeah.
Cool. There's a question from Louis Titchall. He's from Sasri, and he and I are very passionate about mineral compositions, and he's asking about whether we've investigated any mineral components in cane juice, and he's referring to such components as potassium.
Yeah, we have never tried to match it to the potassium. We've never tried to develop an equation for it. It should work. The interesting thing with NIR is NIR actually, the potassium doesn't absorb any NIR energy. However, when it's in solution, the potassium actually changes the way the water sits in solution. That's the simplest way of describing it. So that when the energy is absorbed by the water, that energy absorbed by the water attached to a potassium is fractionally different. So you can pick it up indirectly. So yes, you can. I'd love to do it, but I don't know what the value of it would be. We don't use potassium as a control parameter.
Yeah, I think as a research tool, though, Stephen, it'll be quite useful, because we know that potassium is one of those molassogenic compounds that attracts a lot of sucrose to molasses.
Yeah. And
you'll see in our SASTA annual review next week, the fact that the molasses losses keep on getting higher. So it'll be useful to see whether excessive potassium fertilizer usage might be contributing to that.
NIR is used to analyze for fertilizers in soil and stuff like that. So it is used, but it's actually a slightly different technique. If you want to just look at in minerals or in soils, you actually need a mid-infrared spectrophotometer, not a near-infrared spectrophotometer. But having said that, it does work in solutions, so we can make it work.
Great. Yeah. I think we'll pick up with that conversation with Louis outside of this webinar. Yeah. There's another question from Rainer. He's from the Ilovo head office. He was previously at the Nutsburg factory, so he's speaking about Dextran being good or bad would be great on DAC to a certain, if it can be used as a cane supply monitoring parameter, especially so in the Midlands where we know Dextran can be quite high at certain times.
Yeah.
He says that like purity, it'd be great to pick up, the bottom of the log cane consignments. So the really bad cane consignments.
That is one of
obviously
the things.
We could possibly reject cane based on that.
That is one of the objectives that I have to do in this year in terms of looking at that from the SteerCom, and one of the things that's in our ARC. So it is part of this year's research program.
Yeah,
using information that I already have. So yeah.
I think just to further that comment, I think it only takes a very small batch of bad cane to gum up the factory. I think it's less than sort of 2.5% of your cane. So if we can get rid of those really bad consignments, I think it'll be of great use to the industry.
That is also part of what Sinet and I are doing with that deteriorated cane.
Quite right.
Thing, which hopefully we may go to Nutsburg to go and get samples this year, if we're lucky.
Okay, so there's a comment from Clive Soji as well. So he's from Tonga Hewlett. The end of his message says great work SMRI. So thanks, Stephen. He also just a general comment. There is greater need to fast track cane deterioration detection to make it easy and quick. For example, ethanol determination, if you make that more easier for moles to use. So I think the equation that you've got currently might be useful. I don't think a lot of people know that it's available, so maybe you can just comment on that.
Yeah, so it's all of our members have that equation. If you don't know how to use it, contact Rowena. She will gladly teach you and show you how to use it. She loves doing that. And use it. Don't take the values as an absolute value. It's a rough value. It's roughly 3,000 or it's roughly 10,000. But it will tell you qualitatively that is bad and that is okay. So yeah.
So I know Rowena is listening. She's in the webinar. So maybe one of the things we could do is just put together a little communicate to industry, and we'll issue that to everyone as to how to enable that equation and how to use it.
They should have it enabled because I'm pretty sure we put it on.
Okay, good.
Yeah.
All right. So then how to use it. Stephen, that's all the comments and questions that we have in the chat. Is there anything else that you wanted to pick up on?
No, I think that's about all. It's as you can see, this is a bit of a passion of mine. So I love this type of thing. So bring it on.
Okay. Stephen, maybe just to end off with a bit of a teaser, if you could let our audience know what to expect from the NRS probably in the next season or so.
Who knows? There could be lots of things. There are lots of things that are going on. Some of them we can't say too much about, but look, ideally, yeah. To me, the cane deterioration one is being fast tracked. So I suspect that that you may well see something very quickly happening with that, which will be very useful.
Janice, the SMRI CEO, wants to know whether any of our members has been using the DAC ethanol equations. So I can tell her that yes they have.
They do. Yeah, they do.
And it's been particularly useful with the arson cane that's been processed recently, and also the frosted cane as well.
Yeah, they are using it because we're in contact with them.
Then we'll just end off with the one last question from Waneka. So Waneka is from Malawi. I think it's from the Nchalo Mill still. He wants to know, are we in a position to now rely on NRS solely in CTS for cane payment purposes and for typical sugar factory analyses used for official reporting or factory performance calculations? So,
okay, in terms of the second, you should be able to, the second part of that question, you should be able to answer, Sean.
Yeah, so certainly, Stephen, I think the NRS, it's been put together so we can use it for factory control purposes, and that's what our members have been using. So there's no issue with that.
There's no issue. Okay.
Yeah, but I think in terms of official reporting, you know, where you need COAs and that kind of stuff, you'd still have to perform the MC and then obviously send your samples through to the SMRI.
Yeah, I'm not sure if that's what they're talking about there, or if they're talking about it. It says factory performance calculations. So, but we're doing that now anyway, because that's what the factories are running on. But I'd like to just comment on the CTS cane testing service type stuff. The mixed juice equations are some of the most robust equations that are available. I have spoken to many people at many conferences around the world, and they are all amazed at those equations. That they work incredibly well. They are very good at predicting. They are very precise and very accurate. You need to just decide in your own country, seeing this question came from
Malawi.
You need to decide what official method you are going to want to use, and who has the say in what official method is used. Those equations work very, very well. I would have no doubt using them. No problem. I would use them. But so, yeah.
Okay. Yeah, Stephen, I know there's a lot of confusion actually about the SMRI-NIRS system and the system that CTS is currently trialing on cane, basically. And I think that's where maybe Waneka is also trying to direct his question towards. You know, whether the CTS NRS system is ready for cane payment purposes.
You need to speak with CTS about that.
Yeah, so maybe we can just say just that, the fact that CTS is still trialing the unit. So it obviously has to go through a number of industry committees before it's passed. The benefit of that unit basically is that you can test 100% of the cane coming into the factory. And that's its major sort of vantage point. And somebody in Malawi, it might be actually easier to implement a system like that compared to maybe in South Africa with all of the.
Yeah, I don't know. Yeah. Okay, so what you got to remember is that there are two ways of doing this. One, you can use the existing DAC method, where you go and take your cane and chop it up and go and do a pole and a bricks and a whatever. All right, that our equations will handle that. No problem. Okay, so you can take those, take the mixed juice and handle that. The other system is the one that is being trialed by CTS, which is similar to what is being done in Australia. And that is to take a glass, it's not a glass sheet, it's a sapphire sheet, with the cane, the shredded cane running in front of it, and you do a reflectance on that cane. However, the thing with the CTS one and the Australian one is that they only report on pole and bricks. They do not report on sucrose. So now I don't know how that impacts Malawi or not, but in South Africa it's a big issue because the cane payment system is based on sucrose. Sure. So you've got to take that into account as well.
All right. All right, Stephen, we'll leave it at that. Thank you very much for the time that you spent putting together the presentation and delivering it to our members. I'm sure that they've all appreciated it, and there's some good comments in the chat if you want to have a quick look. Just to let everyone know that this session has been recorded, so we will pop this onto the SMRI website for you to view at a later stage. Thank you all. We'll have another webinar in about a month's time, which will be looking at using our mini Nooch and the NRS system to improve factory performance. And we look forward to you joining in on that one. So stay safe, everyone, and keep well.
Cheerio all.
Thank you. Thanks, guys.